Um, so as part of the IEEE Sensor Council, we started a optical sensors cluster monthly webinar. Today we are very fortunate to have Dr. Minghang Yang. He is a very one of the world leading researcher on fiber optic sensors. So today topic is draw tower fiber Bragg grating FBG array and its industrial applications. So Dr. Minghang Yang is currently a professor and directs the National Engineering Research Center for Optical Fiber Sensing Technology at Wuhan University of Technology located in China. He received a PhD in physical electronics from Hozhang University of Science and Technology in 2003. From July 2003 to December 2005, he was with the Fraunhofer Institute for Applied Physics and Precision Mechanics in Jena, Germany, as a postdoctoral visiting scholar. After that, he worked at the Berlin University of Technology, Germany, as a research fellow. He was a technical program committee member, TPC member of the 23rd and 24th International Conference of Optical Fiber Sensors (OFS) in Spain and Brazil, a subcommittee member and session chair of OSA topical meetings on optical sensors 2013 in Puerto Rico, USA, and optical sensors 2014 in Barcelona, Spain, an international steering member of the 5th Asia Pacific Optical Sensors in 2015 in Korea. He is also a guest editor of the IOP Journal Measurement Science and Technology and the Springer Journal of Photonic Sensors as well. He is currently serving as a topical and associate editor of the IEEE Sensors Journal. He has listed more than 200 publications in peer-reviewed journals and has been invited to talks to international conferences such as OFS, APOS, and OSA topical meeting in optical sensors. So we are very fortunate to have him today. Uh, uh, thank you for your time in Hong. Yeah, please go ahead. Yep.
Okay. Okay. Thank you for the introduction, dear Chair. It's my pleasure to be invited here to present our recent work on joint tower fiber Bragg gratings. And it's also my great pleasure to join this IEEE Sensors Concealed Optical Sensor Cluster, especially for such a monthly webinar. Okay. My name is Minhong Yang from the National Engineering Research Center of Fiber Optic Sensing Technology and Networks, Wuhan University of Technology. I will make my presentation with the four points. First of all, I would like to give you a short introduction of our institution. And second, I will say something about our drone tower fiber grating technology. And the third part is our application works with on RD for fiber Bragg grating array for distributed temperature sensing, distributed strain sensing, distributed acoustic sensing, and also distributed multi-parameter sensing. And also I would mention some about other optical fiber sensing research and development activities. Okay, with this slide, I would like to show where are we in China. I think most of you should know China where it is in the worldwide, but you don't know Wuhan maybe. So this is a map of China. Actually, we are sitting just across the Yangtze River, which is the longest river in China, and also is as you can see from screen here, this is the circle point of the Wuhan, and where Peking is somewhere here and Shanghai is somewhere here. So we are just in the middle part of China. We have very small in our province. There's very famous Three Gorges Dam, and also we have very nice inner city lake in our cities. So This image show what where we are in Wuhan, and this building is also all the buildings. It's National Engineering Research Center for Fiber Optical Sensing Technology. We are the one of the National Engineering Research Center in China, research on the fiber optic sensing technology, and especially we are developing technology systems for for uh, uh, fiber sensing applications, especially for safety monitoring, for bridge, tunnels, and undergrounds. Now we actually in our institution we have 56 faculty members, about 200 master and PhD students. So these are some of our facility in our institution. We can make the very traditional fiber fiber micro machining and also fiber simulator for FPG writing, and also we have our specially designed fiber coating system and also fiber FPG writing systems. And also we have some other spectroscopy, and also for especially we have a fiber drone tower which can be used for continuously writing FPG arrays during the fiber drawing process. So actually in our laboratory we developed from the very beginning of the sensing principle, and then we develop also sensing sensitive materials and also key defilements, and later on the sensing network, especially folks with special interest for industrial engineering, and also we provide the so-called turnkey solutions for industry partners. So second part, I will talk you about the drone tower fiber grade. Grade. Yes, I think first I want to show something about the background. Everybody should know that 5% technology is widely employed in many industrial applications. For example, for the oil tunnel, and also for the railway and coal mine, bridge, electrical networking, and so on. Many applications. But nowadays, for the distributed technology, we use the most based on the scattering technology. For example, Rayleigh scattering, brilliant scattering, and Raman scattering for temperature measurements. So for such a distribution measurement, we have the much more distribution measurements along the fiber. You don't need to make the sensors. Fiber itself is a sensor. Well, for such kind of scattering technology, we know that such scattering technology has very weak signal, and somehow you have the very slow response time, and also since the signal is weak, so you have the somehow the no signal to noise ratio, and therefore you have the very low precision and limited networking parameters. Another technology based on what wavelength division multiplier, the so-called FPG technologies. But FPG technologies, you have a very strong signal and also fast response, which can be used to generate the networking for multi parameters, for example, strain, temperature, and relative heat humidity, and so on. Many parameters can be monitored with the FPG platform. But if you use FPG, due to the limited the night source, you can only measure with limited points, and also such FPG typically is fabricated one by one, and then welded one by one, which means the high transmission smooth, and also sometimes you can't have very high mechanical properties. So if we combine with such technology for FPG, you have very strong signal to ratio, and where distributed technology is low, and also measurement accuracy for FPG is high, and which can be also have a very fast speed and the long distance. Well, The point for FPG technology, you have the point measurement. So not the network capacity is very limited. Normally, we say less than 100. And for distributed sensing, they have for sure it's very with a very huge capacity for large distance. And well, typically it's based on the rainy scattering, and then the intensity is limited. Therefore, they have many disadvantages. So, well, in the industry, we need a very large capacity with high precision and also long distance, and with also with fast response. How can one make that in one system? As I mentioned before, for the traditional FPG technology, you need to script the protecting layer, and then with the Simon laser to write the FPG, and then you make the recoding, which is it's really time consuming, and also it's not suited for large capacity for long distances. Well, with a very lower limited mechanical properties with a lower reliability. So in our technology, in our laboratory, we are trying to make such two technology in one system. That means we can write artwork FPG during fiber fiber drawing. Normally the reflectivity is 10 to the power minus 4, which means that we can make continuous FPGs. Normally can be more than 10,000 FPGs during fiber drawing process, which since the FPG is very weak, so we have very low transmission power loss, and there's no splicing point along the fiber, which means that the mechanical is mechanically robust, and we can combine with such DTM and WTM technology in one system. Well, and the challenging for that, the idea is simple. That we have drone tower, and during the tower, you can make the simulator to write FPGs during the fiber drone system. That's the idea. But the challenge is that how to make it in practice, especially for very large capacity with the industrial production. The two technologies. First is the teleport, which is the interface, which is based on two paths to interface with the fiber gratings. And this one is very tricky, but you have to tune or control the path distance exactly, which is very much challenging. Another technology is based on face mask. That means use of face mask, you can make the FPGs based on face mask. But the challenging for drone tower FPG, that the fiber itself is moving. It's not static. That means you have to make the examinator just in one shot, just with one simulator exposing since the fiber is moving. And then because fiber is moving, you have to control the whole system in very static. The challenge also for that's because fiber is moving, and then they have kind of a vibration. If the vibration exists, and then you can make very good FPG arrays, and then you have different FPG. The tolerance for the FPG central wavelength is not exactly the same, which is also that could be the problematic for really applications. So for our technology, we try to make the to consider the both dynamic fiber pooling and static propagation of the rays in one system, and then we use many technologies to make the drone tower stable even during the drone process. This is just a composition of the system. I show you before for the traditional dynamic propagation of the gratings. You have the very different FPGs array, which is not good enough for real application. And later on, we are able to make the industrialized dynamic propagation gratings with very good consistency and repeatability of the propelled large capacity arrays with the wavelengths normally consistency less than 0.1% nanometers. So also because this is a single laser pass dynamic grating preparation, and the single pass, which means that the energy is limited, and in that way we can make the very weak FPG, and also the intensity of FPG can be tuned based on the requirement of what kind of its applications, and then the total transmission loss could be less than 0.5 dB per kilometers, which is good enough for industry applications. So the third part I was talking about FPGA arrays we made in our institution. We can make such kind of FPGA arrays, but the cabling is also very challenging for FPGA arrays. We are able to make the different cable system. For example, temperature cable, sensing cable, for vibration sensing cable, and strain sensing cable. It's based on the also we have the built-in process force technology and the vibration response sensitization technology, and also for the moisture sensitive materials coating technology for moisture measurements. And this is a very traditional FPGs, which based on the point measurement. And this is the cabinet for our technology. So this screen, this FPG arrays is already used for example, thousands of sensors, which is traditionally you have the many such kind of components. But here it's just a cable, but the cable itself is it's integrated with the thousands of temperature sensing, strain sensing, and so on. And the technology we use also here is based on the WDM, TDM technology. That means in this we have a different area. With different area, we can use a different wavelengths, and also we can use the same wavelengths in different area. It's based on both. It's possible for us. And this screen shows the temperature distributed temperature sensing with the 6,000 FPG arrays with the three different central wavelengths. And this is one 2,000 FPG array, and this is another 2,000 FPG array, and this is another 2,000 FPG array, totally 6,000 FPGs. So each point means one FPG. FPGs can make such kind of FPG arrays just in one cable, and this is demonstration of the temperature measurement. We keep the third part and the first part and third part of in the temperature oven, and then we change the temperature. You can see the increase of the wavelengths with the temperature increase. Whereas in the middle part, we keep it in the without the heating process, just in the room temperature, and the wavelengths all keep it the same. This is a very good demonstration for the distributed temperature sensing, and such kind of cable can be cabled in with different materials for real industry applications. For example, this is one example with the for OPGW cable applications. And this is just one feed demonstration for the temperature measurement, which we use the oil field test for the downhole temperature measurements. As you can see, the increase of the temperature with the position going down the downholes. Another FPG technology for the distributed strain sensing, as you show here, each part is a FPG, but FPG is already pre-stressed with So can you hear me now?
We can hear you, yeah. But yeah, if you share the
Okay,
slides again,
sorry,
yeah,
sorry.
no problem.
Just now it's already okay. I'll continue. So you can see my shared screen, right?
Not yet. Yeah, it's still loading, I think.
Not yet.
Yeah.
Okay, moment.
Yeah, I think it looks okay now. Yeah, we can see your slides. Yeah.
You can uh
Yeah, we can see. Yeah, please go ahead. Yep.
okay. You can see okay. I'll go ahead. So
Yeah,
you can
sure.
see my screen, right? Okay, yeah.
Yeah. Yeah, we can. Yep.
Okay, good. So this is the so-called pre-stressed strain cable with a different cabin for distributed strain uh, measurements. And this is a demonstration of such kind of cable for the bridge intelligent bridge health monitoring. We have a local bridge in our local city with a span of 65 millimeters, and then we install the strain fiber on the bridge, and then to with the every BG each then we can measure the strain deformation with a different track loading. For example, if the truck loading is 18 pounds and 14 pounds, the deformation, the strain deformation, or the stress measurement of the with our strain distributed strain cable system measurements. This is just for the with such technology, it's possible to monitoring the strain, the bridge health deformation for the real applications. This is our bridge, local bridge, which is already installed with such distributed strain cable for sensing and for health monitoring. And um, especially this is the we have the different track as you can see here. This is the location of the track with a different area, especially for the newly built bridges. Is for the static loading test. In such case, we can test the train bridge deformation with different loading and to simulate and to test its healthy status, especially compared with the design with the very beginning original design. So this is also the imagine of the strain measurement during the strain and during the different time with the curvature of the deformation of the train, the bridge under the different loadings. Especially, we can record the history deformation of the bridge. And so with such kind of intelligent, with such kind of a very, very big data, we can get the history deformation of the bridge, and then we can tell what happens in the bridge, especially for the long-term healthy situation monitoring. Okay, the third part is the distributed oxygen sensing. That means we can monitoring the distributed vibration or acoustical sensing. That's based on the so-called FBG, Fabry-Perot technology. As you see, one can make the FBG arrays, but if you two FBG, we can the two FBG generates a so-called Fabry-Perot structure. The Fabry-Perot structure, the length, the void,
It seems like he has internet issues. Let's see. He'll come back again.
Sorry, and I use another computer, yeah, because I don't know what happens with my computer.
Yeah, seems like internet issue. Yeah, we can see your slides now. Yeah, please go ahead. Yep.
Okay, okay. Yeah, I don't know what happened with I use another computer now. So I will continue with my slides. I think I have already talked about the
Yeah,
distributed
no
arc
problem.
sensing. Yeah, this slide. Yeah. So I will continue. So moment. Okay. So the so-called distributed arc sensing is based on the Fabry FPG based on Fabry parallel structure. And then the Faber parallel structure is sensitive to phase sensitive. So we measure the distributed phase shift, and then we get the oxidative signal. Well, for such kind of technology, you have to use the so-called because the two FPG should generate the mirror structure. And then with the broadband, we use the very special broadband FPG. That means the chirped FPGs for fabrication sensing. And this is the intensity of the OTDR spectrum of the ultra-weak FPG arrays. You can see different with the different time we have different intensity, which is the typical FPG intensity, which and then we compare with the 1.7 kilometer fiber spliced with the 1.8 kilometer FPG range, especially for the reflective signal with the FPG signal, we have very low intensity, but with the ultra-weak FPG range, that means that we have the very weak FPG reflectivity, even the FPG reflectivity is low, but when it's compared with the scattered signal, it's still strong enough. So such kind of district technology can be used for the smart metro, which means that you can monitor in the the uh, the, the discrete altitude waves for some, and then with the intelligent processing of big data and to get many information, for example, identification and location of the illegal operations, damping assessment, and also geological change and so on. This is a real application of our technology for the Wuhan Metro underground uh, monitoring system, which is for safety intelligence system monitoring. Especially since the cable is no it's installed along the track, and then we can get different uh, noise and also the FPG peaks during the subway. It's moving, and then we can monitoring the different the in to get the information for the of monitoring the vehicles and tracks for, and then we can know the health station of the vehicle and also the tracks and such kind of for example, this is the monitoring of the problematical series number with a different period stake, and then we can uh, get the information about what happens for the train and also happens for the truck. And that means for for the healthy monitoring. And this is also another example for the intelligent motor vehicle based on the so-called the envelope, with the typical normal envelope, you can get the very uniform curve or spectrum. But with the abnormal envelope, you have different information. With such kind of information, one can get the what happens, just the abnormal point and also the abnormal events happens for the subway. Another distributed oxygen sensing is for oil field tanks. For example, we generate the uniform of the DPS system with with artificial LPG cables with the more than 1,000 with kilometers, and then we use such kind of cables for downstairs vertical spectrum protect profile test to get the underground obstacle measurements, especially for the preform monitoring for distributed sensing for the downhole system. And then we can such kind of technology also for the hydrogen fraction monitoring, that for the oil production. That means we if the water go inside the rocks, and then we use the fraction monitoring to get what happens in the production. For example, for the fraction, we with a very dense structure, strong signals. Without fraction, there's no even the no very there's no the signal is weak, and then if the dense also the event is proportional to the fraction production. Um, in such way, one the feed oil production, they can get the information what happens and what it goes, especially for the fraction process, especially with the such chemical technology can be used for the production optimization. Another technology is based on the distributed matrix sensing processing. We can use the so-called multiplex sensing with such kind of FPG arrays for temperature, strain, and also fabrication in just in one fiber system, in one fiber system. The the technology used here is based on the FPG. FPG itself as a temperature or strain measurement, and two FPG. Between two FPG, we use a vibration measurement for example for the acoustic sensing. And this is a demonstration of our distributed optic sensing for hydrogen pipeline leakage detector. We can install the fiber along the pipeline and then to monitoring the temperature change to make the strain change and the measurement and also the vibration measurements and to get the information what we need. Especially for our such technology, we can make the district temperature sensing and district acoustic sensing just in one system. That means just one system with property with capacity to measure strain and temperature just in one system. Where for the conventional district sensing or district acoustic sensing or district temperature sensing, they are based on two different systems. And this is also for the downhole acoustic sensing. Also for the oil field test in somewhere China for the vibration during the fracture production process. And then such kind of system can be also used to monitoring the temperature with the during the fraction process. Uh, so I will mention two slides about our technology we are developing. We are also developing hydrogen sensing, temperature sensing, and heat beam sensing. Especially for hydrogen sensing, we developed the special materials for hydrogen sensitive. And then such kind of materials can be coated or can be mounted on the FPG tip of FPG side surface to monitor temperature hygiene, and also for similar technology for humidity measurements. This is one of our system for the dual pass hygiene temperature and measurement. We can measure temperature from the very uh, for example, we use the balanced or with a compensated hygiene measurement system, which can be very precise for temperature measurements. Especially, we can measure temperature from ppm to tenths of ppms for the hygiene measurements, and also we are able to measure the temperature and the humidity sensing component and system for different really applications. And this is just one of our demonstration, our measurement system for the hygiene for real for our laptop system. And also such kind of technology is also very widely used in some industrial applications. For example, for the coal mills industrials and for the hygiene combustion. So to conclude my talk, I would say drone tower technology with FPG arrays enables significant increase of multiple sensings with numbers more than 10,000. And FPG array sensing technology enables the distributed temperature sensing, strain sensing, oxygen sensing, and even for multiplexer sensing on just in one fiber. And distributed market sensing with the drone tower technology would be a new alternative for the future. And now, finally, thank you for your attention.
Yeah, perfect. Yeah, thank you very much. Yeah, it's very helpful for us. If you have any questions, yeah, please type in the chat box or unmute yourself, and then you can ask your questions. Anyway, this presentation will be made available in the IEEE Sensor Council's YouTube channel, and then anyone can go and watch later uh, if you want. Let me check the chat box. Okay, maybe if they're thinking, I have one question. So for the hydrogen sensing, until now, you demonstrated only one point sensing, or you demonstrated quasi-distributed or distributed sensing for hydrogen sensing?
Uh, you mean hydrogen sensing, right?
Yep, yep.
Yeah, for hydrogen sensing, we are mainly based on the point sensors. Point
Okay.
but we have the closely distributed point sensors for multi-point measurements. But later on, we are developing for the fully distributed hydrogen sensor with special coatings along the fibers, especially with the drone tower technology, maybe in the future. Mm.
Yeah, 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 yeah. That will be good. Yeah, yeah. Very good.
Yeah,
Uh,
thank you.
Yeah, thank you. Yeah, I think if there's no questions, yeah, if you have any question, yeah, please reach out to Mi Hong, yeah, later. Thank you very much for your time. Yeah, have a
Okay,
great
thank you.
weekend.
If you have any
Thank you, and
further questions, we can keep contacting per email or any other ways. Yeah, very nice
sure, sure.
to yeah. Okay.